Hi, I'm Karthik Swaminathan, also from IBM Research, and be presenting some of the work we have done on developing this early stage reliability and security estimation tool for RISC V processors called ERASER. As I don't need to elaborate on this, reliability-aware design operation is essential for pretty much every domain, ranging from servers, hyperscale systems, down to embedded systems, autonomous driving systems in particular, mobile phones, and so on. If you have processors say at either end of the spectrum, say for high performance or server class machines like IBM Power 9, or of course like a RISC V Rocket core in this, actually the Ariane core in this case, say which could be fitted into something like an autonomous driving system, they are obviously vulnerable to several sources of errors. One of the main issues is radiation-induced soft errors. Particularly those the cores deployed in the field are vulnerable to alpha particles, beta, gamma rays, and so on. And this can cause random bit flips and consequent errors. In addition, there can also be targeted errors due to something like row hammer attacks, where bits, particularly memory, can be targeted bits can be flipped, and this can cause major security violations. So we need a methodology to incorporate protection and mitigation against these kinds of errors right from an early stage of design. And that's what we propose to do in the ERASER tool, which is an open source framework for this kind of reliability and security evaluation. As a larger context, even the preceding two talks from Luca and Skylar were in the larger ambit of the DSOC program, which is sponsored by DARPA, and which looks at an entire stack of building heterogeneous SoCs. And in this talk, we particularly focus on the security and reliability aware design, in this case for CPUs, but can be easily extended to a whole bunch of hardware units as shown here. And just an overview, some of the terms, of course, like Fertile, which Skylar has already gone through. And I would like to focus on just on a couple of metrics here. One is RAS, which is the way processors are usually qualified in terms of the resilience and reliability. And the other one is residency, which is the amount of time in which a latch's state remains unchanged. So this is a key metric which we'll be considering for our reliability evaluation. And we evaluate it as the total number of execution cycles by the number of data switches in this case. Finally, we also have failures in time, which is the failures in 1 billion hours of operation. And that's a standard industry standard metric for determining the processor vulnerability. So it's possible to carry out this kind of evaluation at various stages of the processor design, right from an analytical stage down to the building a cycle-accurate simulator, and the RTL simulation, FPGA-based emulation, and finally the processor fabrication. However, you can notice that at the first two stages, there's not enough not enough information on the physical design, and particularly in terms of the latches, their size, and their vulnerabilities. And the last two stages, it's probably too late to affect any changes. It can be argued that you can have some significant design input even at the FPGA stage. But we focus in this case on the RTL level simulation stage. And we can actually look at some of the latches and carry out these simulations and run this methodology to evaluate the vulnerability of latches and proactively make design changes to mitigate them. So because of this, we have the ERASER tool, which can evaluate the RAS readiness of a processor and even the effectiveness of existing protection techniques and whether we need even more protection techniques. So this thus provides a comprehensive framework for such a vulnerability estimation, even at such a pre-silicon stage. So this is an overview of some of the components used in ERASER. One of the components used is Microprobe. This was a tool developed primarily for IBM systems, looked at Power and Z systems in particular, and it was an automated microarchitecture-aware test case generation methodology. And it has been used heavily in various stages of design in these IBM systems. The SER Miner tool, which I developed in collaboration with colleagues, was an automated generation of these kinds of SCR stress marks for particularly for the power tool. And these were based on utilization or clock switching based metrics. And we ported this to RISC V, which is the kind of overview of what we present in this talk. And the HCR miner tool looks, as I mentioned, looks at these switching files and generates latch level switching statistics. And finally, there's a fault injection tool, which that was developed by Skylar here, and it looks at statistical and targeted fault injection into latches within a RISC V core. And this leverages some of the fertile passes that he had talked about, and it's got a wide range of applicability even in this space. So as an overview of the entire ERASER tool flow, we generate single instruction test cases for all the instructions in the RISC V ISA. This is run through a RISC V base core model. In this case, we adopt the Rocket core, but this can be easily extended to multiple other cores since it's just dependent on the particular ISA. We generate VCD files from RTL level simulations, in this case using the Rocket Chim emulator. Generate macro level or RTL module level switching information and use that to get residence information, which is used to generate a stress mark. These stress marks are then you run through a similar flow of emulation macro level switching information to generate a set of vulnerable latches. And finally, you have a targeted fault injection methodology on these vulnerable latches using the sheaf tool. This will finally give us a final set of latches that we can deem to be vulnerable and determine what kind of protection that needs to be adopted for these particular components. So from the previous slide, so some of the key features of ERASER, we support the analysis of latches by means of RTL simulation. We have switching residency analysis aggregated at the RTL module or macro level. We use these to generate stress marks to evaluate the worst case vulnerability, particularly to minimize the derating of latches in case of in case of a soft error strike or a radiation strike. We then have obviously the validation platform that I mentioned. And finally, as I mentioned, we demonstrate on the Rocket core, and we are in the process of extending to other cores as well. So as an overview of the exact methodology for generation of the stress marks, the basic idea for the software stress mark would be one that minimizes the derating or maximizes the exposure of a bit flip error. And this would happen when a maximum number of macros are vulnerable predominantly through the execution. So for example, if you have a bunch of macros that have high degrees of residency across their latches, as opposed to a few macros with the residency concentrated only on a few latches or few macros, the former would be much more vulnerable. So we have two metrics, the latch residency and the macro, what we term as macro coverage, which we need to maximize. We use a kind of greedy algorithm by which we select each macro depending on the residency, as I will show here. So we have assumed that we have on the vertical axis we have the macros, and we have and every instruction and the residencies corresponding to each of these instructions. So for example, R11 would be the residency of macro 1 when instruction 1 is run. R12 is residency of macro 1 when instruction 2 is run, and so on. And here we want to focus on the most vulnerable macros. So we use a parameter called rho, which is the residency threshold. We can vary rho depending on how it's a user parameter, and this can be fine-tuned to maximize the effectiveness of the generated stress mark. And it's a user-defined parameter between 0 and 1, and we only consider the residencies of those macros that are above the rhoth percentile in terms of the maximum residency. So for example, if the residency of macro 2 is less than, say, rho percent of the maximum residency seen across all instruction, we will just set it to 0. And based on this, we determine a joint SCR metric in terms of the macro coverage, the residency, and the CPI instruction. In this case, just for the purpose of an initial evaluation, we considered single CPI instructions because it obviously depends on the clock frequency. So as a joint SCR metric, we just consider the product of the macro coverage M, and the residency R. And this looks at the entire ISA, looks at the entire processor, but we can actually adapt it to a subset just of a few instructions or a few macros to focus on the targeted errors that I spoke about. So if you want to look at a particular set of vulnerable bits or vulnerable latches or macros, we can do that as well. So as we go on selecting macros one by one, we will kind of knock out those particular macros from their instruction, and this will continue. We continue successively to select instructions until all macros are covered. And the sequence that is generated in this manner is our skeleton sequence, which can be used to generate the test case. The test case is basically an infinite loop running these sequence of instructions one after the other. So we have some sample results. So we evaluate on 3 metrics: the residency, the coverage, and the joint metric, which is the product of the two. The evaluated workloads, we look at the entire ISA, around 140 instructions of the single instruction test cases. And these we use as the baseline, so we consider the average metrics and the peak metrics of all the instructions. There are also ways to generate workload proxies for entire workloads like spec, which is an ongoing work. And finally, we also have the stress mark that we determined, and we try to calculate the metrics for this. As you can see, the stress mark is clearly worse than the maximum of the instructions in all these 3 metrics. This is a single data point, which is around 99% row. We can, as we vary the residency threshold, we can get different values and get even higher values of these metrics for the stress mark. So this, as we mentioned, is initial work. It's available public, and we encourage people to contribute different cases, different scenarios, different algorithms to them. There are ways we would like to extend it to beyond SCR, beyond soft errors, to voltage noise, thermal aging induced errors. Look at further kinds of architecture enhancements, look at uncore parameters, look at interconnects, the memory controller, and other components as well. We also would like to adapt application level derating considerations into the fault injection. This is purely latch and microarchitectural level analysis at the moment, but there is obviously a lot of work at the architecture and application level, which we would try to incorporate as well. And finally, the fault injection methodology is pretty basic, in which we run single tests on latches. We would like to develop an infrastructure for large-scale fault injection simulation experiments to have a statistically significant number of results. So that's another part which is ongoing. So to summarize, we have this early stage modeling tool of a vulnerability called ERASER, which we use for characterizing process vulnerability at the latch level. We use it to generate and evaluate stress marks that maximize the latch residency and determine the most vulnerable latches. We also, it comprises of this fault injection based validation toolchain. I have a brief, so these are some of the links, key links. This is all available on GitHub. It's all supported by the Apache 2 license, and it's free for use. Many of the tools which are developed, many of the other tools like Microprobe Sheaf, and of course the Rocket Chip, which is our evaluation core, are also can be accessed through this GitHub module. I have a brief demo for this. Hopefully the sound doesn't give up on me. Okay, I don't think the sound is working, but that's okay. All it shows is the way to set up the workload. We just run a example test case. Oh God. Unfortunately, it seems to cause my laptop to hang for some reason. how am I doing on time?
5 minutes.
Okay.
Yeah.
Then might as well give it a shot.
More than 5 minutes.
Okay. Yeah, I think it doesn't seem to like this. Yeah. Yeah, sorry about this. Oh, okay. Okay, maybe I can just run through this. So the first task would be to generate the single instruction test cases. So these are all the instructions in the RISC V ISA. So this we generate these test cases and compile them. It's stuck again. Yeah, this shows the entire workload being compiled. We then run these through the Rocket chip emulator, generate VCD files, which we then parse and generate latch activities. And these latch activities are then used to aggregate, are aggregated to get macro level statistics and to get this kind of a 2D macro versus instruction residency profile that I had shown. Yes, sorry about this. Yeah, and then finally we use these macro statistics to generate the stress marks. So these are these are the examples of the macro and instruction level statistics. So for each macro we have the residency value across the entire ISA. So these are for instruction 1, 2, and so on for every single instruction. And as in, a few of them are 0 because they have been thresholded out, as I mentioned, because the way we had depending on the value of rho. And finally, we use this to generate the stress marks. Yeah. So according to the algorithm that I described earlier, these were the instructions that were output. So SC, SC.V0, FCVT, and so on. And these we use this as the basic skeleton to generate our test cases, which is run in an infinite loop. And these are then again evaluated, run through it, and the list of most vulnerable latches are obtained from this evaluation. We then would carry out a fault injection methodology as I described in this. Of course, I didn't include the fault injection because we would like to do it for a more larger scale environment. So yeah, so sorry about the demo, but yeah, this is a basic overview of the way the tool works. We would encourage you to contribute to it and be happy to take any questions. Any questions? Yep. Any questions? All right.
Yeah.
Okay. Yeah.